Our next application of the principle of inclusion and exclusion and this delicate Poisson sieve that we've discovered is classical. It's historical. It goes back to the year 1708, and de Montmort wrote about this among several other problems of this ilk that he had considered. This one is called Le Problème des Rencontres. And translated, it means it's a problem of matchings. I'm going to phrase it for you in its classical, whimsical statement. I'll give you perhaps a more sober reassessment of what the problem really is. Imagine a setting where we have n individuals and they're all wearing hats. I don't know, this promptly dates me because who wears hats these days? But perhaps an ascot. But let's suppose that we have n individuals wearing n hats. The hats are taken off, shuffled, and handed back to the individuals at random. Now, some questions now arise out of this. One question could simply be, if you hand back the hats at random, what are the chances that nobody gets their own hat back? And a more nuanced version of this question. What are the chances that exactly k out of n individuals get their hats back? Of course, this is purely whimsical. I could imagine a group of sailors on shore leave who, in a fit of playfulness, enter an establishment, and when they leave, just grab somebody's hat, put it on, and leave. And now you've got a jumbling of hats. If you want a more sober version of this problem, imagine that you have n articles, each of which is associated with, let's say, a location, a place, an envelope. If these articles are allocated randomly, what are the chances that none of the articles goes to the intended location? What are the chances a certain number, k of them, go to the intended location? So this is sometimes called a matching problem. So now let's jump in and do an analysis of this problem. What is our starting point? Inevitably, what is the sample space for the problem? Well, let's strip the problem of all the irrelevant trappings, hats and sailors and individuals and so on and so forth. What do we have at heart? We have n individuals. Let's label them, give them names, 1, 2, 3, up through n. And what do we have next? Each of them is allocated a hat. Let's call the hat allocated to individual 1, pi 1. The hat allocated to individual 2, pi 2, and so on. The hat allocated to individual n, pi n. Why pi? I'll come to that in a moment, why I chose this particular nomenclature. So the first person could perhaps get the third hat, in which case pi 1 stands for 3. The second person perhaps got the 11th hat, in which case pi 2 is 11. And perhaps the last person got the second hat, in which case pi n is 2. What can we discern about the numbers pi 1 through pi n? Well, each of them is a number from 1 through n, and no two numbers are the same. The same hat can't go to two people. In other words, we've discovered that the sample points of this experiment are permutations of the numbers 1 through n, and that explains the nomenclature, why I chose pi, for permutation, of course. Each permutation then gives rise to a sample point. Remember, to specify a sample point, you have to give me an object whose specification eliminates all chance connotations for the problem. The moment you tell me all the values pi 1 through pi n, I know precisely which hat each of the individuals received, and there's nothing now left to chance. And therefore, these are exactly the sample points. How many permutations are there? Well, naturally n factorial. So this is a finite setting. But the number of sample points grows very, very, very quickly because the factorial function grows quite rapidly as n increases. Very well, so at least now we understand the sample points are very simple to characterize. They're given by permutations of the numbers 1 through n. What is our next question? Well, inevitably, what is the probability measure? And of course, in this setting, there is no reason to believe that any one permutation is to be favored over any other permutation. And therefore, we have a combinatorial setting where to each permutation, we allocate equal mass. And what is that mass? Well, the reciprocal of the number of terms that are in the sample space, the size of the sample space. In other words, each permutation is allocated atomic mass 1 over n factorial. So far, so good. This was not very hard at all. But of course, the next question, the million-dollar question, what are the events of interest? Well, naturally, whether the individuals get their hats or not. So let's promptly put in place some terminology, some notation here. Let A sub 1 denote the event that the first individual got his hat back. In other words, pi 1 is 1. Let A2 be the event that the second individual got his hat back. And generically, let A sub j be the event that the jth individual got his hat back. We should very quickly take stock for a moment. What is an event? Well, an event is a subset of the sample space. What is the sample space? Well, systems of permutations. What then is the event Aj? Aj then corresponds to that subset of permutations where the jth element in the permutation was j itself. In other words, the hats got spread out, but the jth hat stayed where it belonged. All the other hats could be assigned willy-nilly in any way whatsoever. And therefore, we identify with the event Aj those permutations where the jth element of the permutation was j itself. Okay, this is clean and simple. Now we're making progress here. Before we try to do an analysis, we should take a step back, as it were, and take a look at the situation that is developing. These events are quite simple to characterize individually. The events seem to have a certain symmetry property. That is, every individual, as far as their hats are concerned, has the same look at the situation in some loose sense that every other individual does. The random allocation of hats is conferring symmetries upon the problem. But these events are not independent. And to see why this is the case, all we have to do is consider the simplest of the settings where, say, n is 2. If you only had 2 individuals, then if the first individual gets his hat, in other words, A1 occurs, that forces that the second individual also gets their hat. In other words, when you have 2 individuals, knowing A1 tells you everything about A2. Of course, so these events are now tightly coupled together. The saving grace here is going to be the following, that if we have a large number of individuals, then saying something about one of them has a very modest, perhaps negligible effect on what happens to the others. In other words, we're going to discover that these events are only weakly dependent. And that is going to set the stage for the emergence of a Poisson sieve. But we are getting ahead of ourselves. So let's put in place some more terminology, some more notation. Let's promptly write down x sub j to be the indicator for the event Aj. X sub j is 1 precisely when the jth individual gets his hat, and 0 otherwise. And the events that we are interested in, first, that nobody gets their hats. Well, A1 does not get his hat if the event A1 complement occurs. A2 doesn't get his hat if the event A2 complement occurs, and so on. The event that nobody gets their hat, of course, is the intersection of the complements of each of these events Aj. In terms of the indicator variables, this says that the sum of the indicators is, sadly, 0. A more nuanced version of this is when the sum of the indicators takes a given value k. If this occurs, then precisely k individuals get their hats. And of course, we'd like to try to compute such probabilities. So let's start. Naturally, our first question now is, can we set up a proper inclusion-exclusion formulation. And for this, we're going to have to take a look at the inclusion-exclusion sums. George Pollier would recommend that we start with the simplest version of the problem that we don't yet understand. And following his sage advice yet once again, let's start with the simplest of the inclusion-exclusion sums, that corresponding to a single event. What can we say about the first term? So pick a generic event, let's say A1. What is the probability that A1 occurs? Remember, A1 was the event that the first individual got his hat back in this random allocation. Of course, this is the probability of that subset of n tuples where the first element is locked in at 1, and all the others can be anything else they want. How do we compute this? Well, the cardinality of the event A1, the size of the event A1, the number of permutations that trigger A1 is easy enough to characterize. Remember, the first element is fixed at 1. The first hat goes back to its owner. But then you have n-1 remaining hats to allocate. And they can be allocated willy-nilly. And so there are exactly n-1 factorial sample points in the event A1. Out of a total of n factorial sample points, we have a combinatorial setting. And therefore, the ratio works out as it must to 1 over n. The first individual has a chance 1 over n of getting his hat back. Of course, the moment you've done this particular analysis, it's clear that exactly the same analysis works for any individual. The probability that A2 gets his hat is again 1 in n, because the second element in the permutation is held fixed, and the remaining n-1 elements are allowed to vary, and so on for any individual. And therefore, the inclusion-exclusion sum, S1, corresponding to singletons, is simplicity itself. There are n possibilities for the singleton, n ways of selecting the individual who we are looking at. For each such individual, the chance of his getting his hat back is 1 over n, and therefore the first term in the inclusion-exclusion formulation, S1, is exactly 1. Okay, this was perhaps too simple. We should look at a slightly more complex setting to see how we can settle our intuition. So let's look at the case of the second term in the inclusion-exclusion sum. This is going to require pairwise intersection probabilities. And let's start with 1 for definiteness. Let's look at the first two individuals, 1 and 2. What is the chance that both of them get their hats back? What is the probability of A1 intersection A2? What does that event mean? Well, it means we're looking at all subsets of permutations where the first two elements in the permutation are fixed. The first element has to be 1, the second element has to be 2, and the remaining elements can vary arbitrarily. And therefore, A1 intersection A2 has got exactly n-2 factorial elements in it. And therefore, the probability of this event is n-2 factorial divided by n factorial. And that gives you the reciprocal of n times n-1. And some of you might recognize that in the denominator, what I really have is a falling factorial. It is n to the 2 falling. Okay, a fancy way of describing a simple object, but bear with me. Okay, and once you've done this, it now becomes clear what we have to do. The second inclusion-exclusion sum, S2, sums over all pairwise intersections, but every pairwise intersection behaves exactly like A1 intersection A2. Each of them has exactly the same probability of occurrence, and therefore S2 is the number of pairs, n choose 2, times the probability that any particular pair of hats is returned. And this gives us 1 over 2, or 1 over 2 factorial. Having seen the cases for the first and second terms in the inclusion-exclusion sums, we're now coming to a right understanding of how this thing is going to play out. Let's very quickly jump forward to a generic term, say the jth inclusion-exclusion sum. Remember, this means that we're going to look at j-wise intersections of the events at hand. The events being, of course, that the individuals get their hats. Let's pick one particular j-wise intersection for definiteness, so we can get an understanding of how this thing is going to play out. So let's say we pick sailors 1, 2, 3 up to j, individuals 1 through j, and ask, what is the chance that all of them get their hats back? What is the probability that these j-specified individuals get their hats back, 1 through j? The story now is clear, because this means the intersection of A1 through AJ corresponds to exactly the following event. All those permutations where the first j elements are fixed. The first element has to be 1, the second element has to be 2, the jth element has to be j. And the last n minus j elements can be anything they want. And so this immediately gives rise to a probability given by n minus j factorial over n factorial, cancel common terms in numerator and denominator, and we discover a falling factorial in the denominator. The probability that j specified individuals get their hats back is the reciprocal of the falling factorial n to the j falling. With this in hand, we're ready for the jth inclusion-exclusion sum. Let's just write it down. Again, the symmetries in the problem tell us that these probabilities are unaffected whichever group of j individuals you choose to look at. There are n choose j such groups of individuals, and therefore the jth inclusion-exclusion sum works out to be simply, elegantly, beautifully 1 over j factorial. We can't really have hoped for anything much cleaner than this, especially when we started out at the setting where there was a worry that the lack of independence in the events A1 through AN was going to cause trouble. No matter. We've got a simple reciprocal factorial capturing these inclusion-exclusion sums. Let's promptly put it all together. Let's begin with the simplest question. What is the chance that none of the individuals get their hats back? So remember, A1 complement is the event that the first individual does not get his hat back. A2 complement, the event, sadly, that the second individual does not get his hat back. AN complement, the event that the nth individual does not get his hat back. The probability of the intersection of all of these is given by the basic inclusion-exclusion alternating sum. We promptly put in our reciprocal factorials in here, and now we've got a clean and simple expression. S0 is 1 by Fiat definition. S1 is also 1, but we're going to write it as 1 over 1 factorial. And then we have a 1 over 2 factorial, a 1 over 3 factorial, and so on, with alternating signs in front. Does that remind us of something? Of course, the moment we have these factorials in the denominator, that is going to start suggesting an exponential function. In which case, we're looking at a power in the numerator. Well, what is the power? Oh, this is the simplest of the possibilities. We are simply taking -1 to integer powers. -1 to the power 0 is 1. -1 to the power 1 is -1. -1 to the power 2 is +1. And so -1 to integer powers is going to give you alternating pluses and minuses. And so what you've got is a truncated exponential series whose exponent, whose parameter, is -1. But the factorials in the denominator tell us that this series is going to converge fearfully fast. And therefore, these truncations are already going to be very, very close to the limiting object. And therefore, what is the limiting object? It is just e to the power -1. Very approximately 1/3. In words, the chance that nobody gets his hat back is approximately 1/3, e to the power -1 if you want to be more precise. And this approximation is good even for very small values of n because of these factorials in the denominator. Even for n equal to 4 or 5 or 6, you'll find that the approximation, e to the power -1, is very, very close to the actual inclusion-exclusion alternating form that I have up there. And so we've discovered something beautiful. Here's a slogan that de Montmort discovered in 1708. The probability of the obverse of this event, the probability that at least one individual gets his hat back, is approximately 2 in 3. 1 minus e to the power minus 1. And this is almost independent of the number of people that you're looking at. Even for very small values of n, you're going to get this as a very good approximation. This is unexpected, perhaps. You look at this as well. That is neat. I didn't quite anticipate this, especially when you have a large gaggle of sailors and you're tossing hats to them at random. We wouldn't anticipate that something so simple and elegant popped out of this by looking at an asymptotic analysis. Let's look at a more general case, and it's not going to be much harder at all. So let's just put these inclusion-exclusion sums together. What's the probability that exactly k individuals get their hats? And we've got a new inclusion-exclusion alternating formulation. Plug in the fact that these inclusion-exclusion sums are reciprocal factorials, and now it's just a question of algebra. Write it all out. You find that various terms cancel, numerator and denominator. Put it all together. You find that every one of those terms has got a reciprocal k factorial in it. Factor it out. And then inside the round brackets, you discover, oh, wait a minute, I've just found a truncated exponential series again. And that entire thing in the round brackets is going to be approximately e to the power minus 1, and therefore, here we go, Bob's your uncle. The probability that k out of n individuals get their hats, and nobody else does, is approximately e to the power minus 1 divided by k factorial. And this result is going to be valid almost independently of the size of n, even for very modest small values of n. Now, the way I've developed it, it looked accidental, but of course it's not accidental, because we realize, wait a minute, let's take a look at what those inclusion-exclusion sums really are. They're of the form of a reciprocal factorial, 1 over j factorial. Okay? But 1 is the same as 1 to the power j. So what you've got is that these inclusion-exclusion sums are of the form of a fixed number to a power, 1 to a power, divided by a factorial. But this is exactly the province of the Poisson sieve. And so here's our slogan. The number of individuals who receive their hats, even for modest values of n, is governed by a Poisson law with expectation 1. I ask you to step back and savor such a beautiful and elegant result, which emerges so unexpectedly from what looks like a complicated mix and mess of a problem. This also points out why we are really doing a metaphorical sieve. A lot of individuals don't get their hats back. In fact, most individuals don't. The chance of getting a hat back, even for modest values of n, is quite small. It's only 1 in n. This is a rare event. And what governs the number of rare events that occur? It is a Poisson distribution, and in this case, a Poisson distribution with expectation unit. Let me go on and give you another classical example. I must apologize in advance. I'm feeling whimsical today. This is going to be our next lecture.